So given that we can't take the derivative of that likelihood function on its own, we're going to do something else. And to understand what we're going to do, which is going to be the EM algorithm, let's first imagine, we're going to use a technique called majorization-minimization. And that idea is as follows. Let's say we have some function, which in this case is going to be our log likelihood function. What we're going to aim to do is, this is going to be an iterative algorithm where we're optimizing the log likelihood of theta with respect to theta. What we're going to aim to do in each iteration is to come up with some surrogate function for L of theta that we can optimize. And it's worth noting that actually you can think of all of the optimization methods we've been using as doing more or less this. So if we are doing gradient descent, you can think of gradient descent as defining a linear approximation to the function and then following that linear approximation for some short distance. Similarly, Newton's method, or more generally second order methods that we didn't talk about, they define a second order approximation to the function and then optimize that. We're going to define instead a lower bound to the function, which might look something like this. So specifically, we're going to define some function that we're going to call q, which has the following properties. By the way, just one note here is that for just this section on EM, we're going to imagine that we're trying to maximize a function rather than minimize it. The reason for that is just to be consistent with the literature. Turns out literature on EM is all about maximization, where literature on most other types of optimization is all about minimization. So just to make things extra confusing. So notice here that we've written the log likelihood itself, not the negative log likelihood or the loss or whatever else that we'd want to optimize. So we're going to define this function q that again has the following properties. It's going to have two properties, and q is defined in a way where we define this auxiliary variable. So q is a function of two values that we usually call, we might call them theta 1 and theta 2. Here we've written them as theta with no superscript and theta with superscript t. So we're going to require that q of theta, theta t is always less than or equal to the log likelihood with respect to theta with no subscript. That is the first argument. And we're going to require that if you give it the same argument, theta t, then that equals the log likelihood of theta t. So we haven't defined what that function is, but let's imagine someone handed you a function like this. Then our optimization algorithm is going to be that at each iteration, we take the maximum of q with respect to theta with no subscript, that's this first argument here, of q theta theta t. So another requirement in practice of q is that it must be computationally efficient to take its maximum. So either we need to be able to analytically take its maximum with respect to this first argument, or we have to be able to quickly use some other algorithm like gradient descent or Newton's method or whatever else. So then we take, we define theta t plus 1 as this maximum, and then notice that at the next iteration we use theta t plus 1 as the second argument for q. So you can think of this as kind of a two-step process. In step 1, we take the last iteration's parameters and stick them in the second argument, and in step 2, we take this maximum. So just to go back to our picture here, so here we are at iteration t. So this blue dot would be theta t. Then we define this function q theta t. So notice that we're holding theta t fixed here, so it's just theta that gets to change. So we're going to optimize q with respect to theta. That's going to give us this point here, which will become our new theta t plus 1. And then we're going to define a new q theta t plus 1 and continue the algorithm. And then we might end up here. So this strategy of majorization-minimization, this is a general strategy for optimization. This works anytime you can define a function q that has these two properties. Again, that when you put the same argument twice, you get exactly the value of the log likelihood function or whatever function we're trying to optimize, and that when you vary the first parameter and hold the second parameter constant, then you get a lower bound to the function. It's not too hard to show that this is guaranteed to improve your objective, your log likelihood with each iteration. So let's look at that. So if we start with some parameters theta t, and well, we can just rewrite that as q of theta t, then we optimize q with respect to the first parameter. So we're going to define theta t plus 1 to be the maximum in the first parameter. So now we end up with q of theta t plus 1 comma theta t. Now notice that this must be greater than or equal to q of theta t because this is specifically designed to be the maximum. So we could end up with the same parameters. That's what happens when we converge. But before we've converged, we're going to end up with a better value of q than we started with, that we get from q of theta t. Now notice that this is a lower bound on our likelihood function. So if we look up here, this thing always has to be less than or equal to L of the first argument. So that tells us that this thing is no better than log likelihood of theta, not theta t, but theta t plus 1. And then this, by the way, equals q of theta t plus 1, theta t plus 1. Same thing we have here, and we can continue to the next iteration. So this shows that this majorization-minimization algorithm will always improve our log likelihood from iteration to iteration. And by the way, among the two steps, each step is also guaranteed to improve the value of the Q function. You can see that from these less than or equal to signs, or greater than or equal to signs. That's not true for algorithms like gradient descent or even Newton's method. Those methods generally improve the objective, of course, because that's what they're intended to do, but they're not guaranteed to. For example, gradient descent can sometimes overshoot and give you a worse objective value than you started with. But that's not true of majorization-minimization. These algorithms, and this applies to EM, of course, because it's an example of a majorization-minimization algorithm, majorization-minimization algorithms always improve the objective from iteration to iteration. That means they tend to be very fast in practice. Generally, when we can define these algorithms for a given problem, it tends to do better than other methods, like, say, gradient descent. And they tend to be quite easy to debug in our implementation because we have this guarantee. If your gradient descent algorithm doesn't improve the objective from iteration, could be because that is just doing what gradient descent is supposed to do, or it could be a bug in your algorithm. If that ever happens with majorization-minimization, you know it's a bug in your algorithm. So that turns out to catch lots of bugs. I know from personal experience, this is a very powerful tool when you're trying to debug an algorithm like this. Okay, so that was majorization-minimization. That's the general idea behind the EM algorithm. Now let's look specifically at the EM algorithm. And again, EM applies in the case where we have latent, unobserved variables. So let's go back to that log likelihood expression I showed at the beginning. So again, we have our log likelihood, which is defined as the sum of the likelihood on each of our examples. But because this isn't defined without also defining our latent variable, we need to marginalize out that latent variable. And again, this thing is tricky to optimize without help, which is what we're going to do now. So for us to be able to use that majorization-minimization strategy, we need to have a lower bound Q function. So let's define such a function. So in order to do this, let's come up with some auxiliary distribution. We're going to call those Q of n. So Q of n is some arbitrary distribution. We're going to define it specifically in a second, but for now, let's just assume it's any distribution we came up with over Z of n. And the textbook doesn't make this explicit, but let's make it explicit in our notation here that Q of n is going to turn out to be determined by theta t. So Q of n is essentially a function of theta t. So, okay, but for now, forget about that. We can just define any distribution Qn. Now, we've rewritten this expression here. We've just multiplied it by Q of n over Q of n. We just multiplied that in here. So this thing is equal. Now we're going to use a trick to come up with a lower bound. And that trick is called Jensen's inequality. We haven't proved it here, and it's defined in the appendix, so I encourage you to check that out. But we're just going to trust the textbook for now on this. So what we've done with Jensen's inequality is we've pushed the log inside this sum. So again, we can't do that that doesn't give us exactly the same answer because we can't in general push logs inside sums. But because of Jensen's inequality, it turns out to be that this thing is less than or equal to this thing. So we get a less than or equal sign here. Now we end up with the two sums on the outside, and we end up with this expression on the inside. Qn of Zn times log of this ratio. By the way, another way to write this is like this. So the way we got this is we took this term and we split it into log of P minus log of Q, because remember that a log of one thing divided by another thing is log of the first thing minus the second thing. And then this second term gave us this here. This is the entropy of Q of n. I would have liked to include the chapter on information theory. I think information theory is a really interesting topic. You can take a whole course on it, and I encourage you to do so. Unfortunately, we don't have time this semester, but that's not too important here. Just the important thing is just that this is some quantity that's a function of just Q of n. Notice that this term here, we have this guy and this guy. Notice that we don't have anything that depends on P in this term here. And then the first term, that's this one here, we have the same thing, just minus the Q of n. The textbook writes it like this, as this expectation. We can be more explicit about this. We might write this as the expectation that Z of n is distributed according to Q of n. Of this thing here. So notice that this has the form of an expectation. It's the sum of something, this distribution, of this particular value on the inside. The value on the inside happens to be log of P of y of n, z of n, given theta. Okay, but that was a long way of saying that we've defined this function q that's a function of two things, theta and these auxiliary distributions Q of n, and that this is a lower bound on our likelihood. So this is going to be our Q function. Now, for Q to fit into our majorization-minimization framework that we defined a few slides ago, it has to have two properties. The first is that it's a lower bound in the first parameter on the thing we're trying to optimize. And that's what we just proved. So we're good on criterion number 1. For criterion number 2, we're going to require that we define this auxiliary distribution specifically as the probability of z of n given y of n and particular values theta. And specifically at a particular iteration, we're going to use theta t here, which is going to give us a q of t. Now it turns out, this isn't obvious, we have to prove it, but I'm going to omit the proof here. The proof is in the textbook. I encourage you to go through that. It turns out that if you define q of n like this, then big Q of theta t q of z given theta t, I'm putting the theta t here just to make it explicit. That thing turns out to equal L of theta. So that is that this inequality here is tight. That is, it's exactly equal and not greater than or equal to. So again, that's not obvious. You have to prove that. And that occurs when we define our Q of n this way. Okay, so we did all this work to define this function Q. Now, Q is only useful to us if we can use it in this majorization-minimization framework. And specifically, it has to be the case that Q is relatively easy to optimize in theta. Because remember, at each iteration of our majorization-minimization of our EM algorithm, we have to optimize Q with respect to theta. So we have to optimize this thing here. Notice that when we do that optimization, this term we don't have to worry about, because if we're optimizing with respect to theta, then this second term doesn't involve theta at all. So it's just this first term that we have to optimize. So it has to be the case that this thing is reasonably easy to optimize. And it better be a lot easier to optimize than this thing here, because the whole point of this was to avoid having to take the derivative of this thing and trying to optimize it directly. It turns out that it tends to be much easier. So in a few slides, we're going to do a couple examples, and we're going to show how we can take the derivative of this term and in fact optimize it analytically in theta relatively easily for many problems. So again, the EM algorithm works. It's great in the situation where you have a hard time optimizing this thing and taking its derivative directly. And that's usually going to be the case, again, because it has this log outside of a sum. It's useful if you find a way to take this derivative. So I would say a lot of papers on kind of probabilistic modeling using latent variables end up, the main point of the paper is once we do this EM trick, then we, in this paper, figured out how to take the derivative of this term. So you have to do this step, but this tends to be easy for many probabilistic models. Okay, so that's the first thing. You better be able to optimize this with respect to theta. The second thing you have to do is you have to be able to figure out what is P of z of n given y of n theta t. Because we have to define this for in order to plug it in to our Q function. Again, this tends to be not too hard. This amounts to probabilistic inference of z of n. And there are a lot of methods for probabilistic inference, some of which we've talked about so far, some of which, in the case of, for example, probabilistic graphical models, we're going to talk about in a little bit. Okay, so just to reiterate, we end up with our EM algorithm. You can think of EM algorithm as iterating these two steps. The first is to figure out what these Q of n variables are, these auxiliary distributions, and that amounts to a probabilistic inference over z of n given the parameters theta t. And then the M step, the second step, is to figure out what is theta t plus 1 by maximizing Q with respect to theta q t. And then we repeat using t plus 1 here. One thing that's worth noting, when Q of n, or when z of n is a discrete random variable, for example, in the case of clustering, we're going to look at this in a minute, when z of n is discrete, we can just evaluate this probabilistic distribution directly. That is, we do our probabilistic inference and we end up with a vector of k values where those are the k probabilities. But what if Q of n is a continuous, or sorry, Z of n is a continuous random variable? Then Q of n is some probability density function. So it's a mapping essentially of each possible real value to some probability. You can't represent that explicitly. So what we have to do is find sufficient statistics or some values where, given those values, we can define what this function is. So in the case of often Q of n is going to end up being a normal distribution. So this is going to turn out to be, you can represent it using the sum and the sum of squares of a particular function. So we're going to look at, in not our first example, but our second example is going to be that case.